an associate professor in the Department of Electrical and Engineering at Columbia University. From 2016 to 2019, he was a senior postdoc in computing and mathematical sciences at Caltech. Previously, he was a junior research fellow at St. John's College in Oxford, where he also earned his DPhil in 2012 and holds bachelor's and master's degrees in the University of Reading. He's won multiple accolades for his work, including IEEE Transactions on Network Control Systems Outstanding Paper Award and L4DC Best Paper Award. So today, James is going to talk about collaborative learning for control. So I'll leave it to you.
Okay, thanks very much, Morgan, for the invitation to present part of the ACE network. So today I'm going to be talking about some of our recent work, ongoing work, in fact, that's been carried out in my group over the last 2-3 years, specifically collaborative learning for control. So before, I just want to acknowledge the following people. The sort of heavy lifting of this work was done by Han Wang and Leonardo Toso, 2 PhD students in my group at Columbia, as well as more recently, Dong Lin's got involved in some of the meta learning, which is related to some of the things I'll be talking about today, and my colleague Aritra Mitra from North Carolina State University. So the question I want to ask in this in this work is, when does it help to collaborate when trying to solve a problem? Right now, in theory, collaboration always seems like a good idea, but that's only really true if all the participants, if their goals are aligned and they're bringing the relevant expertise to the problem. Right? You think about when you were maybe an undergrad and you were doing labs, and you just start working with your lab partner, and then in walks someone 10 minutes late who is, if they join your group, is just going to slow you down and make your life worse, right? This is an example of when collaboration isn't necessarily a good thing. So we would like to tease out, in a control context, when exactly does collaboration pay off, and specifically what are the benefits? Can we tease out exactly what the pros and conversely the cons are of collaboration? So the framework we're going to be using to answer this question is federated learning. So federated learning is a distributed learning paradigm, and it sort of originated in the supervised learning setting. So this is the easiest setting to motivate it in. Then I'm going to specialize it to an optimal control setting in a second. So as the sort of canonical example is, imagine you have a set of hospitals, each with their own patients. A patient goes to a hospital, their medical, they're screened, they take a bunch of tests, and then their medical records are used, or the results of these tests are used to infer whether or not they have a particular disease. So what you'd like to do is you'd like to build a model takes in all the patient's data, and it learns whether or not the presence of whether or not there is a patient has a disease or not. The problem with this is, in something like a medical setting, you can't just share medical records. Right? Medical records need to be kept private. In order to build useful models, you need a lot of data. And so if you don't have that much data, how do you sort of build a model that is going to capture, is going to sort of capture the distribution of the data that you really need? And so the idea behind federated learning or collaborative learning is that each, I'm going to call it client, but hospital in this case, will build a model based on the data of the patients it has. And so in this case, a model could be a neural network. So each hospital will agree on a shared upon architecture for the network. They will run some local learning algorithm to build a model, right? And then instead of sharing data with each other, because they're not allowed to, and as you know, this might, if this was a real-time application, this could be a large data set, and you don't have the communication bandwidth to share a record. Instead, you share the model. So in this case, you share the weights in your neural network. And what will happen is a server will aggregate, or the idea is the server will aggregate all of these neural network models into a larger statistical model. It will then broadcast the statistical model back to each of the clients. And then the clients will use that sort of aggregated model as a seed to start another round of learning on their own local data. And you keep repeating this process. And the idea is that the aggregated model, whilst data hasn't been shared, the aggregated model has learned data from each of the different participants. Okay, so if in hospital 3, the patients come from a particular back geographical area, then the overall model will reflect that, because that will be learnt by the local model that gets incorporated into the larger model. You can also think of this as being advantageous because it means the global model, the model at hospital 1, technically now has learnt a model based on data that it didn't have to collect or run a learning algorithm on. So there's some efficiency to be shared there. So the outline for the talk is I will sort of formulate this federated learning cartoon in the language of distributed optimization. And then I'm going to talk about how you can apply this to an optimal control problem, the well-known linear quadratic regulator problem. The setting for which is going to be model free. So we get to learn a controller directly from data. So before I get to the federated LQR problem, I'm going to briefly recap some sort of recent learning-based approaches to model-free learning. And then if time permits, the newest part of this work is to look at how this federated problem can work in an asynchronous setting. So for example, in the previous slide, when you're aggregating, the speed at which you can do this is always going to be dominated by the slowest person to communicate their model. So we're going to look at methods that essentially don't require all participants to be sharing their model in order to derive an aggregate model. So, okay, on to federated learning, right? So it's a distributed optimization that specifically accounts for data and device heterogeneity. So whoever's doing the local learning, it's perfectly fine for them to have data that follows a different distribution to the other participants. The amount of local compute might be different across different devices. This idea of data locality, right? So data is never transferred to the server. Okay, the only thing that ever gets transferred between the server and the clients is going to be the model. So there's some notion of privacy. And the idea is that because you run, say, n iterations of training locally at the client, you only need to send the model every n iterations. So it's in some sense, the amount of bandwidth you need to transmit the model is going to be reduced because you're not updating the weights, or at least you're not transmitting the weights to the server at every iteration of the learning algorithm. So this idea of federated learning has been around for a long time. Perhaps it was first used in practice by Google, where they were using federated learning. They were sampling the population. I think there were about 100,000 participants, and it was used for next word prediction. Perhaps a more simple example would be something like linear regression. Right. So in the centralized setting, all the data is in one place, or at least is globally accessible, and your goal is to construct a line of best fit, right? A gradient and an offset. In the federated setting, in this example, we have 3 clients here. And so federated learning would proceed by, first of all, the purple, or in parallel, the purple, the red, and the blue clients would learn their own model, right? They would then transmit the gradient of each of their gradients and offsets to the server. The server would average them, send them back, and another round of learning would proceed. You'd iterate this a few times, and hopefully, if things go well, then you will get a pretty good line of best fit for all three clients. Right, your global average model should do pretty well. So let's formulate this as a distributed optimization problem. So we can actually look at this as a stochastic problem, where we would like to minimize on average this loss function L, which is a function of X. So this is X is our vector of model weights, neural network weights, for example. But it's also a function of this random variable zeta. So L is the loss function, X is what we would like to, the variable we get to choose to minimize the expected loss. And zeta is drawn from some distribution which is unknown. And now sort of hidden in this problem is the distributed nature of it. So let me pull that in now. So we'll assume that there are capital N clients, and each client generates M samples. Okay, so we'll have D1 through M, and each client will draw zeta 1 through zeta M from this distribution P. So how does this, where does the distributed nature of this problem come? Well, we can write it in this form down here. So we would actually like to minimize the average of the sum of these N functions Fi, where Fi is loss function with zeta drawn from client I's distribution. Okay, so this is essentially expanding this problem, written this way is now a distributed optimization problem. And again, we have to solve this problem where we're not allowed to send the zetas to the various agents, right? The zetas are local to the N agents. So the canonical, or the first algorithm that was proposed for solving this problem is called federated averaging. It's not a particularly great algorithm. There are lots of things wrong with it, but it can work well, and it's pretty simple to write down. And so this is why I'm going to present it. It's also kind of the basis for our results later, where we'll build in some theory around it. But the algorithm proceeds as follows. Okay, so at the server side, there are, let's say, 10,000 clients that are going to participate in the learning. The server randomly selects some subset, SK, of the clients, right? So you don't need all the clients to participate. And XK, or X0 at the first round, is the initial global model. And so this model gets broadcast to all the clients that are chosen to participate. Okay, each client, so in parallel, each client sets the global model to be its initial model. And then it's basically just going to run Tor -1 steps of, and the simplest thing to do is just stochastic gradient descent. Okay, so it's going to initiate it from the global model with learning rate eta k. The client I is just going to run a gradient descent algorithm for Tor -1 steps. Okay. After Tor -1 steps, it is going to compare its local model from the previous round to what it just converged to, and it's going to send that difference, so the difference between what it had at the previous round and what it's just learned. It's then going to send this difference, which we're calling delta. Right? So delta IKT, there's a lot of notation here, but this means that this is the client I's update after Tor rounds of SGD. It sends this to the server. Right? The server then waits until all the clients have sent this update. It averages these errors and adds it to, there's a learning rate here as well, and it averages it to the global model. Right? We then assign that global model to the k+1 iterate, and then this k+1 iterate is then rebroadcast to to all of the clients, right? And we do this capital K minus 1 times. Okay, so the idea is that X sub big K, for K sufficiently large, is going to be the global model that has captured the information from all of the clients. Okay, so we're going to modify this to an optimal control setting, right? And the idea here is a client is going to be a system that can be approximated by a linear dynamical system. And the idea is we're going to have all of our clients are going to be linear systems, or things that can be approximated by linear systems that are somewhat similar. So imagine I've got a fleet of drones, and maybe things vary on them, like the payload or the center of mass, or the amount of thrust that can be applied to the throttle. So they're all similar, but not identical. And the idea is if we collaboratively learn as a group, then maybe that will be more efficient than if we all, and robust, than if we learned individually on our own. So before I get to the federated version of the problem, I need to go through the model-free LQR problem. And before I get to the model-free problem, I should probably, just so everyone's on the same page, describe the LQR problem. So everyone's going to understand this. You've all seen this 100 times before, but it's really just to establish notation. So we're concerned with discrete time systems, deterministic, that evolve according to the dynamics xt plus 1 equals axt plus but. The initial condition is drawn from some distribution t, and we're going to look at the infinite horizon case. State has dimension n, input has dimension m, and we need some assumptions on the initial conditions, which aren't particularly important, so I'm going to skip them. But essentially, they say that on average, the initial condition of the state is equal to 0. All right, so the objective, we know that the optimal linear policy is just a static feedback gain k, and so we would like to choose k such that the closed loop is stable and we minimize this quadratic cost, right? So this quadratic cost balances how much the state deviates, and that's characterized by the positive definite matrix Q versus the magnitude of the control input, which is characterized by the positive definite matrix R. So the goal is to choose K that stabilizes the system and minimizes our quadratic cost. The only thing to point out is this set calligraphic K of all stabilizing controllers is in general non-convex, which in the model free setting is going to be a bit of a pain, but we'll tell you how to deal with that later on. Okay, so if we know A and B, Q and R, then we know exactly how to solve this problem optimally, right? First of all, we solve the discrete algebraic Riccati equation for PK. We then use PK to construct our feedback gain K star, right? And we're done. The question is, how do we do this when we don't have access to A, B, Q, and R, right? All we have instead is trajectory data, right? We get to put an input in, we view what the state does, but we don't have an A and a B. Actually, for the purposes of this talk, we'll assume Q and R are known, but that's also no big deal either. All right, so the Riccati approach isn't going to work, but something that might work is to kind of do gradient descent on the objective function to find this controller K. Right, so what does gradient descent look like? Well, we're going to update K according to our existing value for the controller, and then we're going to subtract off some learning rate multiplied by the gradient of our cost function C evaluated at K, right? This is exactly gradient descent. In the RL literature, this is called policy gradient. Okay, so let's keep going with this idea, right? So I can take let's assume we have everything we need to begin with, and then we'll start removing things. I can take my cost function, C, and I can rewrite this, right? I can rewrite this in terms of a quadratic expression that involves the initial conditions, which are drawn from some distribution D, and PK, which is a solution to this Lyapunov problem equation. Okay, so this kind of looks easy to solve, right? Because now I've got a quadratic, but pk is non-convex in decision variable k, so it's not entirely clear we've done anything useful here, right? But anyway, the reformulated problem, and this is one-to-one, this is exact, is I can now minimize this quadratic subject to dynamics plus stability, and my goal is to use this gradient descent type iterate on k to solve this problem. So in order to do that, I should probably figure out what the gradient of the cost function is, and a little bit of algebra will tell you that it looks like this. This is admittedly a mess and in no way looks like it's helped me, but it turns out it actually does. So a few little points of notation here. This sigma sub k, this is the closed loop covariance matrix, right? So this is for a given choice of stabilizing controller k. If I were to run the dynamics forward in time, the closed loop dynamics, then sigma k is nothing more than a covariance matrix, right? It's the outer product of my state vector over all time, right? So if I don't have a and b, this is not actually useful. But turns out we can actually estimate this pretty well. Right, so I'm going to take go off on a minor detour, right? And if I have some function f, then we say it's gradient dominated, right? If there exists some scalar mu such that the difference between f evaluated at x and f at the optimal point, x star, is bounded by mu times the gradient of f squared. Right, so what this tells you is when the gradient of f is small, then essentially the difference between f of x and the optimal point in f is going to be small, right? So this is essentially telling you there will be no spurious local minima, right? We use it in place of strong convexity. There's no assumption on the convexity of f here, right? And so functions that satisfy this gradient dominance property, assuming as well that they satisfy a smoothness condition, what it tells you is that if you just do this, if you run gradient descent, then you will actually get to an optimal solution, even if f is not convex. And that's going to be very useful for the LQR problem. Right, so Mariam Fazal and collaborators showed that actually for any stabilizing controller K, the LQR problem is in fact gradient dominated, and you can even write down what the gradient domination parameter mu is. Okay, and by the assumptions on our initial conditions, this actually tells us that when the gradient of C is equal to 0, then K has to be optimal. Okay, so we're going to use this in order to, or rather, Mariam Fazal showed that if you just run gradient descent, okay, for n iterations, then essentially, if you choose n sufficiently large, then the controller given after n iterations is going to be at most a distance epsilon from suboptimal. Okay, and you can extend this to various other RL-based learning methods, but we're going to stick with our very simple policy gradient method. So this still doesn't get around the fact that we don't have access to A and B, so we can't compute this gradient. So we're going to take a reinforcement learning approach and say that we actually have access either to the system and we can just run the system, or we have access to a simulator that we get to choose some input and we get to observe the state, and we can put this input in and watch it for L time steps, and we can do this a number of times, right? And if we do this a number of times, then we can actually estimate the gradient from this data. Okay, so what this means is that our policy gradient will now take it'll take exactly the same form, but instead of working with an exact gradient, we now work with an estimate of the gradient. And so how do we build this estimate from the gradient? Well, this is called zeroth order estimation. And essentially what it does is we're going to assume that we can simulate the system ns times. Okay, we're going to simulate the system with horizon length tour. And what you do is you take the controller K and you perturb it by adding a random matrix and simulate from the initial condition you know. And if you scale it by the number of inputs, the number of outputs, and R is just how big this perturbation is, then if you average across this, then you actually get an estimate of the gradient. And so the more times you sample it, the more accurate the gradient is going to be. You can think of this U, this perturbation, this is essentially a finite difference method, first difference method, averaged multiple times. Well, there are more complicated versions of this, and we might see one later if time permits. But essentially, whenever we see an estimated gradient, it assumes we have access to a simulation engine that can compute this average. Okay, so the cartoon picture then says, if I give you some controller K, I draw a random matrix U, and I give you an initial condition, my simulator is going to give me some system trajectories. My zeroth order algorithm is then going to give me my gradient. And this problem has been studied in the context of control by many, many people. Some key references are at the bottom of the page. And the point now is for n sufficiently large without a model with high probability, after n, capital N iterations, we have an epsilon suboptimal controller, and this can be done in essentially polynomial time and space. This is somewhat efficient. So getting to the meat of the problem now, the synchronous federated LQR problem. Right, so my formulation goes like this. I now have not just one state space system, I have capital M of them. Okay, and each system might have, or each system has its own dynamics, right? AI is the A matrix for the ith system. Similarly, BI, the A's and the B's can be different across all systems. The only thing we're really assuming is that the initial conditions are drawn from the same distribution, but even that could be removed. And we're going to assume they're stabilizable, just so the problem at least makes sense. Okay, so our goal is to construct a common state back feedback controller, right? So a K that is going to solve all of my, that is going to stabilize and hopefully optimize, at least suboptimally, each of my M systems, right? And also what I would like is for this to be, in some sense, efficient, and we'll get to that in a second. So the cost function associated to this is just going to be, I'm going to deal with the average LQR cost across my M agents. And for simplicity, I'm going to assume the same Q and R matrices in the cost for all systems. But again, we can remove that assumption. It's not a big deal. And of course, we need each system, closed loop system, to be stable. And we need our controller to respect the dynamics of the system. So the questions that arise is this common stabilizing policy, right? So I'm going to have some K that stabilizes all systems. First of all, you know, is it even stabilizing for all the systems? And if so, under what conditions, right? So this has a sort of robust control feel to it. This common policy, ideally, I want it to be close to the optimal policy for all of the M systems that are collaborating, right? If it's a long way from optimal, then, you know, is it really useful? So we'd like to quantify the suboptimality. And I'd also like to know, what is the sample complexity, right? Is the amount of data or the number of trajectories that each agent needs to produce, is it somehow less than if they were to learn on their own? If it takes more data to get a less good controller, then it's not clear that I've done anything useful. And then there's a downstream problem of this is, how does this control policy, how can this be personalized and used in downstream tasks? And we had a paper on this at L4DC last year that I'm not going to talk about today, but we have looked at downstream personalization. So to begin with, it should be clear that we can't expect a solution to the federated LQR problem for arbitrary systems, right? If the A's and B's are completely different, then there's no reason to assume there's a common controller, right? If one system is a bus and the other is a submarine, there's no reason to think a common controller is going to do anything useful. So our measure of heterogeneity or similarity is going to be the existence of two, and you don't need to know these ahead of time, they're just going to show up in the bounds, an epsilon A and an epsilon B, which essentially characterizes the largest difference between any two systems in the collaboration, right? So this is epsilon A is how much variance is there in the A matrices, epsilon B, how much in the Bs. And you can think of this as being somewhat similar to a robust control problem where I have, say, A1 is my nominal system, and then this delta perturbation is some parameter that I don't quite know that changes that I would like to provide robust stabilization and performance to. Now, this is clearly a very bad measure of how different two systems can be. This example, I could say a lot more about this, but I'm going to skip it. But in this scalar example, right, where I just have alpha as the A matrix for one system and minus alpha for the other with the same B matrices, right, then my epsilon A is 2 alpha. And if alpha is greater than 1, then both systems are unstable, but unstable sort of in the opposite direction. And we know there doesn't exist, there fundamentally isn't a common controller for these two systems. So clearly we need some sort of bound on how different these systems can be for this problem to be well posed. And we're going to tease this out. So I'm going to give you the algorithm. It's basically exactly the same as fedLQR, but it has some strong theoretical results that make this practically useful. So again, it starts the same way. So the server is going to broadcast an initial stabilizing controller. So you do need an initial stabilizing controller, and I admit that's a big assumption. We've actually got put on the archive a few weeks ago a paper that tells you how to get this in a somewhat data efficient manner. But for this talk, I'm just going to assume that there exists a common stabilizing controller that is known ahead of time. So the server, capital K, the server is going to broadcast this controller, this initial stabilizing controller K, to all clients. I have M clients. So in parallel, each client is going to assign the global controller to be its base controller. I'm going to run capital L -1 iterations of policy gradient, right? So I'm going to estimate the gradient for system I using my 0th order method. Once I have this gradient estimate, I then do one SGD update, or rather I can do a few of these updates. I can go through this in a little iterations and the broadcast model back to the server, right? So each client for I = 1 to M is going to do this, and then the server is going to average these updates. There's a learning rate eta G. G is for global. I should say there's eta L is the local learning rate, and it's going to add that average to my existing controller, which I'm now going to call capital K N+1. This K N+1 controller is then going to be rebroadcast to each of the agents, right? And we just repeat this process N-1 times, and at the end, I'm going to have a controller capital K sub N. And if I've done my job well, then this thing is going to have some favorable properties. So the cartoon version of the picture, if you like, and this is why I've called it synchronous, is the server broadcasts Kn to each of my M agents. They compute their gradients, they compute their policy update. The server then has to wait until every one of the M systems has sent back its delta before it can update. Right. So one of the drawbacks of this method is if system 2 is really slow, either it has a crappy transmission line or the compute on board system 2 is really slow, then we're always going to be waiting for system 2 because the algorithm does require all M systems to participate. So what can we actually prove about this algorithm? So if we jump to the model-based setting, right? So let's pretend for now I do have the access to the A's and B's. then in that case, the global controller update scheme can be written down, and it has this analytic form. Okay, NL and LG, so eta L and eta G are just the local and the global learning rates. L is the number of local steps of stochastic gradient descent being run, and M is the number of agents. So what we can show is if epsilon A and epsilon B are small, right, that is the systems are somewhat similar, then the gradients, if I look at the gradient of the ith system and the gradient of the jth system, when I plug in the same controller, is actually bounded, and it's bounded by a linear function of my epsilon A and epsilon B. So this is what this tells me is I can use essentially the gradient from system I and J is interchangeable because it's going to be small on the same controller, right? And how small? Well, it grows as a linear function of how different the systems are. So if the systems are very different, this bound is not going to be very good. If they're small, then the gradients are going to be similar, right? And the fact that these gradients are interchangeable is actually what is going to allow this this update rule to produce a suboptimal controller. So here's the cartoon of what's going on, right? If K1 is the set of all controllers that stabilize A1, B1, K2, the set of all controllers that stabilizes A2, B2, and so on. And provided I pick my controller, the initial stabilizing controller in the intersection of this set, then what that tells me is for any controller, any one of these controllers, when I take the gradient, I stay within a radius of epsilon A plus epsilon B of where I started. Right, so I can't have one system that gives me a gradient that's going massively far away from the others. And so what we can do is we can pull this into a theorem, and sort of the informal version of the theorem tells us the following, right? So provided epsilon A and epsilon B satisfy some bound, which I'm not going to write out, but essentially this keeps, this is a well-behaved polynomial inequality, provided epsilon A and epsilon B are chosen such that this quantity is bounded, then after running capital N iterations of my federated LQR algorithm, then the distance between the global controller, the average controller Kn, and the optimal controller for the ith subtask is bounded by this slightly ugly looking thing on the right hand side. So let me break this down, right? If I look at this middle term, this is the initial distance to optimality. So if you look at any analysis of sort of a gradient descent type algorithm, then what you see is some constant less than 1 multiplied by this quantity. And here what you see is you have 1 minus the learning rate times some constant. But the point is this whole thing is less than 1. So as n, the number of iterations, increases, this gets smaller and smaller, which tells me that this distance, this thing contracts, right? So over time, as n increases, this gets smaller and smaller and smaller, and for n sufficiently large, this is really going to be negligible. However, I pay a cost, right? Because my systems aren't the same, even if this goes to 0, right, then I'm still left with a constant that is a function of how different the systems are. Now, fortunately, this bound is relatively well behaved, and so actually we will get an epsilon close controller for every system that participates. Moreover, it doesn't matter how many iterations we run, right? For any choice of n, the controller Kn is going to be stabilizing for all systems. So if I go back to my previous diagram, I never leave the intersection of the set of all stabilizing sets. Again, I can show that if I could run this algorithm for an infinite number of iterations, then my error would be bounded by the heterogeneity squared for all agents. So this is telling us that collaboration is actually helping. These results go through perfectly to the model-free case, right? So what I need to do now is quantify the error between my gradient estimate and the true gradient. And what we can show is, provided when we simulate the system, we simulate it enough times and over a trajectory that is long enough and the smoothing radius is small enough, then actually our error bound looks like this. And so the take-home thing to note here is M is the number of agents in the system, right? So as the number of agents M increases, this error bound decreases. So this tells me the more people that collaborate, provided they are within my heterogeneity regime, the more people that collaborate, the smaller the error is going to be, right? So this is a clear example that collaboration is going to help. Moreover, it's going to help me in the sense that I get a stabilizing controller. So each agent actually gets a 1 over ml speed up per iteration, right? They need 1 over ml fewer trajectories relative to if they were optimizing a controller on their own. The overall sample complexity is improved by a factor of 1 over the number of agents, so that's good. And each agent's sample cost reduces from 1 over epsilon squared to 1 over epsilon squared multiplied by the number of agents, right? So essentially the more agents that participate, the better you're going to do. So here's a quick numerical example. If I have a system with 3 states and 3 inputs, and the heterogeneity is given by epsilon A equals B equals a half, then what you see here is effectively as the number of systems, M, increases, so M equals 1 in red, 10 in blue, green is 50, then what you see is the error, right, between the global controller and we've just chosen system number 1's optimal cost. And you can see as the number of iterations increases and the number of systems increase, I get a much better policy. So the more systems that participate, the faster I learn a good controller. Similarly, now if I fix the number of systems, but I look at how different the systems are, I get exactly what you'd expect, right? As when there's 0 heterogeneity for identical systems, I get the fastest. I learn a controller pretty damn fast relative to when epsilon 1, epsilon 2 around 1.5, 0.65 is actually pretty different. Right? We've seen that this can be the difference between stable, unstable systems, easy to control versus difficult to control. And so I'm very, very briefly going to spend 3-4 minutes talking about how we can now adapt this to the case where we don't really want to be held hostage by the slowest agent in the system. So this is work that appeared at CDC last year. And essentially what's going to happen is instead of the server having to wait for each one of our clients to submit its updated policy, we're just going to say, hey, we are going to wait for the fastest BS batch size, for a batch size of say 10 clients to submit their gradients, and then we're just going to execute our policy, our control policy update based upon that. Right, so you can see how the straggler effect, the slow agent, shows up when we look at when we're in the synchronous setting, because our policy requires all M agents to participate. So what we're going to do is we're going to say, okay, well, we'll just deal with a subset of the systems. And so we're just going to average over the first batch size worth of systems. The caveat now is when we take our gradient, right? If in the first batch, if I have 500 systems, if only 100 participated, then the 101th system is now going to be the first system to participate in the new batch. But the controller KN has now updated, right? So I'm going to have systems that are playing with, when they submit their gradient update, they are now using the global controller from the previous round. So you can think of this as like stochastic gradient descent with delay or with staleness. Okay, so we get rid of this weight, and the questions are, how do you choose the batch size? Like, how much is enough? Will the algorithm even converge? Right? Previously, we knew we could guarantee we would get a stabilizing controller at every iteration. We knew the rates at which it converged. And there's this clear trade-off, right? As the batch size goes to M, you recover the original problem, okay, which means slow aggregation, but you'll get good performance in terms of convergence, but slow wall clock time because you're continually waiting for the slowest system. If you choose the batch size to be really small, then the aggregation step is going to be really fast in terms of the wall clock, but you don't know if you're going to converge anywhere. So there's this trade-off to navigate. And so if you just look at this graph, if you just do the synchronous version of fedLQR, this sort of solid red curve is what we can get. If you don't take into account the staleness property and sort of apply a naive algorithm, then you're going to do worse than fedLQR. And what we can show is that by appropriately tuning things, we can actually beat the synchronous setting in terms of wall clock time. Again, this is what this paper goes into. I'm not going to really get into the details. All I'm going to tell you is that if you assume that all agents eventually produce an estimate, so everyone completes their task and you have some bound for this, then what we can show is that the federated LQR algorithm, where you replace M by the batch size, okay, provided you choose your learning rate, which is now going to be a function of the number of the batch size you can deal with, and assuming that there is this bounded staleness condition, then at every iteration we will get a controller that stabilizes all systems. So that's cool. We've kept that, and it's going to converge to a first order stationary point at the following rate. Right. So n is the number of iterations. So after capital N iterations, remember we want this to go to 0, is bounded by this function, and we can break this down into 3 pieces, right? So this first piece is our initial gap, how far we are from optimality when we started, divided by how big the batch size is, right? So the batch size is going to help us here because it's going to make this thing smaller. This is taking into account the heterogeneity, right? So this is a function of our epsilon A and epsilon B. Again, this gets smaller as we increase the batch size, but then we're left with this the cost of working with stale gradients, right? And so it scales not as a function of the batch size. So this does get better as we run the algorithm for longer, but it scales by the maximum staleness in the problem, right? So if you anticipate you're going to have some very slow agents, then this is going to be large. So as this term and this term goes to 0, this term will dominate. And if this is large, if Tormax is large, then you're going to be within a large sort of ball of optimality. But the take-home message here is that if you run the algorithm for much more iterations, if the number of iterations you run the algorithm for is larger than the number of systems in the batch size, then these things go away and you actually get a nice linear speed up in the algorithm. And again, you can show, I'm just going to give you now the global convergence, right? So the global controller is going to be within epsilon plus a heterogeneity constant of optimal, even when you're running with only a subset of the agents. So the things to keep in mind here are the slowest agent is going to dictate the convergence rate. You still get a stabilizing controller. It will be epsilon suboptimal up to a heterogeneity bias. And in the worst case, you're still getting a linear convergence rate. So I can show some sort of very similar plots here. The red curve is the synchronous curve. So with 100 agents, 4 states, 2 inputs, and a batch size of 20, then, and a Tormax equal to 20 iterations, right? So imagine performing gradient descent where some of your gradient updates are 20 iterations out of date. That's a pretty big delay. Yet still, the red curve, this is showing how the federated LQR algorithm would do. If we look at our asynchronous algorithm, we're actually doing considerably better. We can then look at the effect purely of changing the rate, the staleness rate. So Tormax equals 1. This means basically no delay. 3 and 10, we're increasing we're increasing how slow the slowest agent can be, and you're getting exactly what you would expect, right? As the delay increases, the rate at which the algorithm converges decreases, but it's still doing pretty well. And then finally, you can see, what does the batch size do relative to the performance, where we're looking at iterations, not wall clock time. Okay, so as for batch size of 1, so this is basically purely distributed, you get this red curve, and as you can bring in more agents, right, this 1 over M or 1 over BS is kicking in, and you're getting the much faster convergence rates. So with that, I'm gonna end. Just to go over what we've covered, we've formulated and proposed a collaborative LQR framework. I should say there's loads of work that can be done here. I would love to see more people working on this problem. There's a ton of related problems that I'd love to talk about with people. But the main contribution is we've sort of formally proven and given a simple algorithm that shows that collaboration can speed up learning, and we've taken a first step to removing the problem of dealing with stragglers. Some immediate extensions. So we've looked at the question. We've already looked at the question of meta learning. So that is, given our aggregate controller, how fast can it be adapted to an unseen task? So we've got some results on that. Some open questions are similarity metrics, right? Epsilon A and epsilon B. There's no systems theory in there, right? It doesn't capture the difference between stability or instability, controllability and non-controllability. But what we've got sort of works well mathematically. It would be nice to have a solid systems theory interpretation in there. And we've done nothing in the nonlinear setting, and very little in the stochastic LQG setting either. Both of which these problems become considerably more involved. And so with that, I'm happy to take any questions. If you want any further details, the papers for these two, for the majority of this work, are available on my website. But please feel free to shoot me an email or something if you're interested. And so with that, Morgan, thank you.
Thanks a lot, James. Yeah, so has anyone got any questions? I can start with a question then. Do you see this algorithm as an online algorithm or an offline algorithm?
Yeah, good question. This is very much an offline algorithm, right? So when I let me show you the cartoon, right? This is, so I mean, I would love for the cartoon, right? I'd love for this to be an adaptive controller that is actually working on, being updated on devices on the fly. And in theory, it kind of could be, because that this, whatever controller you have is going to be stabilizing. So your drone isn't going to fall out of the sky. But the idea is really more about data sharing in the offline setting to come up with a controller. Yeah, I think the way I view it is you would learn the controller offline by sharing the data, by sharing the models, and then you would do the personalization, right? So once everyone has got KN, this controller, you can think of it as, imagine you've got a drone. I've got a drone in New York. You've got one in Sheffield, and someone else has got one in Cambridge. I run my drone in my lab. My drone is slightly different to yours. My lab is slightly different to yours. Someone left a window open. And so by sharing the models, we're actually getting robustness. You're getting learned robustness from the robustness that my controller has had to learn. And so you get that for free in this problem. And so after a certain number of iterations of aggregation, you then just want to take that controller and then use that to run locally in your lab. And that you could do online. And then that could be an adaptive controller. Or you could just take that controller and you'd be good to go. But that's the sense that I think of this as being online.
Okay. With the drone example, if you have like the same model, it's easy to say that the systems are close and you group them together. But what if you had a lot of old drones, so the dynamics were like quite different across the fleet? Is there a way of grouping them into subgroups where you can then run this federated algorithm, or would you just have to run it globally and just hope for the best that the dynamics are close enough?
Yeah, that's a really good question. So there's a few things, right? So the epsilon A and epsilon B being small, or needing to be small, and the bound we have, the bound is a somewhat complicated function. So actually, you never really know whether you've satisfied it or not. and it's pretty much all we could prove. We know that if you take larger epsilons and b's, a's and b's, this thing will work, but at that point, the proofs are off the table. That being said, we've also looked at, we do have a different idea of similarity, where you can have, we've shown that like the epsilon A and epsilon B can be absolutely massive, and this will still work. Like, imagine you've got an A and a B for one model, and then you just take a similarity transform. So you have A and B, and then TAT inverse TB. Those are basically the same system, but in this metric, the epsilons are going to be huge.
Yeah.
So we've figured out a way to kind of capture that. But something you can do is, and we've done this, so we've also got the federated system ID paper, and one of the pre-processing stages there is a clustering stage. So there, if you have 1,000 agents, and but within those 1,000 agents you've got like old, medium, and new, you can try and cluster them into old, medium, and new online, and then you would just perform this algorithm on each one of the clusters separately, because that would then minimize the heterogeneity, so they would do better. But we haven't done that yet for the LQR problem. We've only done it for sysid. We're working on it, but we haven't done it yet.
Does that mean there's some sense that if I have 1,000 drones and then I have another drone and I'm about to run the algorithm and I could decide to add this drone to the group or not? Is there some sense based on the epsilons if it's better to add it to the group or to keep it away from the group because the epsilons are too different?
Right. So if the epsilons are very different, you might want to hold off. So what we have done in the meta learning paper that I didn't talk about, right? We showed that if you have a distribution of systems and you subsample, so you've got it could even be a continuous distribution of systems, and if you subsample and you basically run the LQR algorithm on this, you modify the cost slightly, you can prove that on anything else within the distribution, that if you then run SGD for like 1 or 2 iterations, purely on the new unseen task, you will have an epsilon suboptimal controller. And so if the epsilon is there, it doesn't even matter what the epsilon is. Right? I mean, well, it does, but it doesn't need to be. As long as it's part of the distribution, you are okay. If it's completely different, like I say, if you have 10 drones and then a model of a remote control car on the floor, this obviously isn't going to work, right? But you wouldn't really expect it. So there needs to be some sort of similarity. The type of things we imagine things being different would be the payload, right? So if the weight is different, that would show up somewhere. There'd be a mass parameter, probably in multiple spots in the A matrix, or if the center of mass was slightly different, or if the manufacturing defects, it might show up there. It also, if you change the training data, right, and the training data becomes perception data rather than state data, then you can have massive epsilons. But that's kind of a different problem. It's more of a perception problem that we're thinking about, but we haven't really addressed that yet.
So, is there any other questions then before we close the seminar? No?
I should say thank everyone for turning up in the middle of the summer. I'm surprised anyone is here, so I appreciate it.
Yeah, thanks everyone for coming. And so, yeah, I think we'll close the seminar today. I think James's email was in the slides, so if you think of any questions, you can send him an email.
Cool. Thanks, Morgan.
Okay.